everyone. Today's lesson is on probability distributions. This is technically the last lesson in chapter 7. However, we usually use this lesson to kick off a much larger probability topic on distributions called the normal curve. So in your notes packet, you may actually find this set of notes at the beginning of the next chapter. So if you flip past the end of chapter 7 and into, I forget what chapter number it says, but it's a supplement on probability distributions. You'll probably find this at the beginning of that chapter. So take a second, make sure you can find these notes there in your packet somewhere. We are going to start with a bunch of vocab here. And let me see if I can zoom that in for you a little more. If you'd like to pause the video right now and get those definitions copied down, you may. I'm going to kind of talk through all of them, and I think in a lot of them, it's going to make more sense once we talk through it rather than just looking at the definitions. So first, let's clarify the difference between theoretical and experimental probability. You've been working primarily with theoretical probability, which is like mathematical probability. So for example, flipping a coin, the theoretical probability of getting heads is 1/2 because there are two outcomes that are equally likely and one of them is heads, so 1 out of 2. Okay? Experimental probability would be actually doing an experiment and seeing how often do we get heads. So maybe you're going to flip a coin 10 times and you would expect to probably get 5 heads if you were to flip 10 times, but maybe you wouldn't. Maybe you would get 6 heads or 4 heads or something like that. That's what's called the experimental probability, is what do we actually see happening when we try doing this thing. And there's this idea in statistics called the law of large numbers. And part of that law speaks to this discrepancy here, when experimental probability doesn't match theoretical probability. And what that's saying is if you do more trials, okay, the larger the number of trials that you do, the closer and closer your experimental probability is going to get to that theoretical probability. So with that coin flipping example, if you were to flip a coin 10 times, you might get, 6 heads. And then we would say, well, the probability of getting heads is 6 out of 10 or 60% based on our experiment. But if you were to flip that coin 1,000 times and record how many heads you got, maybe you would get, 512, let's say. If you were to do that division, 512 divided by 1,000, it's going to be an awful lot closer to that theoretical probability of 0.5 or 1/2 that we would expect to get. So the larger the number of trials you do, the closer this experimental probability becomes to the theoretical. Okay? So we're going to start talking about something called a random variable today. And really what you need to know about a random variable is they're the outcomes of an experiment, like flipping a coin. But we have to do it in a way where it's numerical, because we're going to use that random variable to turn it into a function called a probability distribution down here in just a second. So maybe we're going to flip that coin 10 times, and our random variable will be how many heads do we get. And then we could say 0 through 10 would be our random variable values. So it's the outcomes of an experiment, but you have to set it up in a way where it's numerical, okay? So the values are numbers for random variables. That's important to know. And so what we're going to do is we're going to take those outcomes, those numbers, and pair them with their probabilities. So we're going to make almost like ordered pairs. So for example, I might say, 4 heads, and we got that, or the probability of getting 4 heads was, 1 out of 6, let's say. Okay, and then we're gonna do that with all of our random variable values. We're gonna make like ordered pairs. Okay. And what we can do is then we can use those ordered pairs to calculate something called the expected value. And I know I'm throwing a lot of words at you right now. We're going to do all of it together here in just a second. But the expected value comes from basically taking each of these random variable values and multiplying by the probability and then adding those together. And really what it does is create like a weighted average for you that would give you an idea of what value would you expect to get the most often? If you were to do this experiment, what do you think the outcome would end up being, mathematically speaking? So I'm going to show you a probability distribution here, and we're going to do a theoretical probability, and then we're going to do an experimental probability distribution. And hold on 1 second while I grab a calculator here. Okay, so I've set up a couple of things for us here. We're going to do a probability distribution, and this is our experiment. We're going to flip a coin 3 times. Notice over here I put x equals number of heads. That's our random variable. Okay, so we're using x to represent our random variable, and that will be the number of heads when we flip a coin 3 times. And I'm going to show you how this would work as a theoretical probability distribution, and then we're going to do it as an experiment. Okay, and I'm going to do what's called a simulation for our experiment. So theoretically, let's look at what our sample space could be. So what could happen if I flip a coin 3 times? Well, we could get all tails, or we could get one head here and then a tail and a tail. Or I could get tail, heads, tails. I'm kind of just working through and figuring out how many ways could I get just one head. And then we could have the heads be the last thing here. Okay. When I'm doing these sample spaces, especially with coin flipping, because it's always like a 50-50 thing, I always kind of establish like these ones, okay? So this is all tails, and then here are the ways that I could get just a single head. And then what I can do from there is I can basically duplicate this by just swapping out heads and tails. So the flip side to getting 3 tails would be 3 heads. Here I could get tails, heads, heads. Here I could get heads, tails, heads. And here I could get heads, heads, tails. And that should be all of my possibilities. By the way, I know there's 8 possibilities because 2 times 2 times 2 would give me 8 different combinations that I could make. Okay, so theoretically, here is my sample space. These are all of the things that could happen. Okay. So from a probability distribution standpoint, we're going to set this up almost like a graph. Okay. And down at the bottom, I'm going to put my values of x, my random variables. So I'm going to put 0. I could get 0 heads. I could get 1 head. I could get 2 heads. And I could get 3 heads. Those are my only possibilities, right? I can't have more than 3 heads if I'm only flipping the coin 3 times. And so this is my number of heads. And then up the side here, this is where I'm going to put my probabilities. Okay, and these are all going to be out of 8 because I know I have a sample space of 8. So this would be 3 eighths, 4 eighths, 5 eighths, 6 eighths, 7 eighths, and then this would be 1. Okay, so 0 heads, that only could happen one way, right? One way out of 8. So the probability of getting 0 heads is 1 out of 8. Probability of getting 1 head, I'm seeing as 1, 2, 3 out of 8. Okay. Probability of getting 2 heads is 1, 2, 3 out of 8. And probability of getting 3 heads is the same as the probability of getting 0 heads, and that'd be 1 out of 8. Okay. So that right there is what's called a probability distribution. Basically, I turn these things into ordered pairs. A couple of things you should know. A probability distribution is never going to be able to come down and hit the x-axis. It's always going to hover just above it. So you're never going to have any negative values, right? Because negative probability doesn't really make sense. Now, this is a situation where my random variables are all separated by these like individual digits. There's no numbers in between. But when we do this in real life situations, so for example, if we were to find the height of 15-year-olds, okay, we know that there's values between 5 feet and 6 feet, right? It's more continuous in between. You could be 5 feet 2 inches, 5 feet 3 inches, 5 feet 2.5 inches. So in those cases, a lot of the times we connect these points with a curve, okay, to show that there's points in between. In this case, it doesn't really make sense for there to be points in between. And then the other thing you should know is if I were to take all of these probabilities, 1/8, 3/8, 3/8, and 1/8, the sum of all of those probabilities is always going to come out to be 1. So if I add all of those together, it has to be 1 because that should cover my entire sample space. Okay. Okay, let me show you what this would look like experimentally. And so what I'm going to do again is called a simulation. And I'm going to use what's called a random number generator. And I don't think you'll run into anywhere you have to do this, so you can just kind of follow along. Under that probability menu, I have this random integer option. And so I'm going to have this choose randomly between the numbers 1 and 2. And we're going to say that 1 is heads and 2 is tails. And I'm going to pretend like I'm doing, I'm flipping the coin 3 times, and we're going to do, I don't know, maybe, well, let's do 10 trials, okay? So 1, 2, 3. So that would be a heads, heads, tails. Okay, 1, 2, 3. That would be tails, tails, heads. This is me pretending I'm flipping a coin, by the way. Okay, 1, 2, 3. That is tails, heads, tails. 1, 2, 3. Tails, heads, heads. 1, 2, 3. Again, tails, heads, heads. It's 5 of them. 1, 2, 3. That would be heads, tails, heads. 1, 2, 3. 1, 2, 3. Gosh. 2, 3. And 1, 2, 3. Okay, so in my coin flipping experiment, this is what actually happened. Okay, so now what I'm going to do is set up the exact same type of graph. And again, my options for number of heads are 0, 1, 2, or 3. This time I'm basing it on this, and this is not technically my sample space, this is the results of my experiment. Okay, and I did 10 of them, so my probabilities here are going to be out of 10. This would be like, we'll go 1/10, 3/10, 5/10. I don't know how much higher than that we're going to need to go. I don't think we need to go all the way to 1, so 7/10 should be good. Okay, so let's count up how many times, if this is my number of heads, how many times did I get 0 heads? I don't think that happened. I don't think I ended up with anywhere I had 0 heads. So that one would be, and I maybe misspoke on that last one. I said it couldn't come down and touch the x-axis. Usually with theoretical probabilities, we don't ever touch the x-axis. It can't dip below, but if you have a probability of 0, which we do in this case, we would say that's a probability of 0. Okay. 1 head. How many times do we get just 1 head? So I see 1, 2. I think that's it. 2 out of the 10. So that's a 2 out of 10. How many times did I get 2 heads? That's 1. I think it's almost all the rest of them. 2, 3, 4, 5, 6, 7, 8. So that's 8 out of 10. Of course, I didn't go high enough. 8 out of 10 would be up here. And then for 3 heads, I didn't get any of those. So that would again be a 0. So you can see that my experimental probability does not match my theoretical probability. And that's okay. That's going to happen sometimes. And again, I didn't really do flipping a coin. I did what's called a simulation of flipping a coin. But the idea is that if I were to do this a bunch more times, if I was to do 100 trials rather than 10 trials, this would start to look more like this. And then there's some different types of math that we can do using this type of data display, especially when we get to the point where we can connect it with sort of a smooth curve and do some analysis that way. Okay? Okay, let's take a look. I think we have one more example back here, but I think Okay, realistically, this example is going to be very similar to this one that we just worked through, okay? Because it's a family with 3 children and we're doing boys versus girls, so that's really going to be the same thing as flipping a coin, heads versus tails. So I do want to talk about, I'm not going to necessarily take all the time to recreate the data display here for you because we just did that, but I do want to talk through this expected value piece. All right, so like I said, this example is going to be really similar to that coin flipping example because it's 3 children with 50-50 shots at boy versus girl. So I just wanted to cover the domain piece of this. We're not going to probably take the time to do the actual calculating the probabilities, but we'll talk expected values. Okay, so the domain of the random variables, if X is the number of boys, the domain is just asking what are our possible values for X. So we're going to say X could be 0 boys, 1 boy, 2 boys, or 3 boys. Now again, in something that's a little less distinct, it could be everything from 0 to 3, including like decimals and fractions and all of that. But when we're talking about numbers of children, there's really no in between, okay? So just real quick, I'm going to jot down these probabilities because we're going to need them for the expected value. But probability of having 0 boys would be 1 out of 8. That's the same as that probability of having 0 heads or 0 tails in the last example. Probability of having 1 boy would be, again, if I think back to that heads and tails example, there were 3 ways that could happen because basically you could have the first child be a boy, the second child, or the third child be a boy. Probability of having 2 boys is the same as this because having 2 boys means you have 1 girl. And so again, you could have the 1 girl be your first child, your second child, or your third child. So 3 out of 8. And then probability of having all 3 boys would also be 1 out of 8. Okay. So we're not going to mess with the construct a histogram because that's going to be similar to the example that we just did. But for expected value, here's how we're always calculating expected value. We're going to take the random variable value, the 0, and multiply by its probability. And then add that to the next random variable value and multiply that by its probability. Okay. And the next random variable value and multiply that by its probability. And the next random variable value, multiply by that's probability. That's the expected value, okay? Now, when we do this, this is not going to be super earth-shattering for this particular example, but there will be others that this actually makes some more sense for. But, and obviously, I don't really need to put the 0 one in there, but I'm doing it just so you see what I'm doing. Okay, and our expected value is 1.5, which really is telling us that if I had 3 children, 1.5 is what I could expect in terms of my number of boys. Now, we know that you can't actually have 1.5 boys, right? It's either going to be 1 boy or 2 boys, but those 2 are equally likely and the most likely, right? So what this is just saying is that if I were to do an experiment with 3, I would expect 1.5 of them to come out as boys, okay? Because of that 50-50 probability. 50-50 probability is really pretty boring in terms of this type of thing, but it would be more complicated to use a situation where, you know, it was a more complex probability. And so for right now, we just want to get you to understand the terminology and the calculations and things like that. Okay, that's really it for probability distributions, or at least the start of probability distributions, and this will springboard you right into statistics next year. So this is kind of where you'll pick up at the beginning of next year. Okay? All right, have a great day.